So welcome everyone to the latest installment of CADRE webinar series. My name is Sharon Yan. I'm representing the CADRE team, which is a cloud platform providing easy to use bibliographic data query and computational infrastructure in the cloud. So the latest news is we just released a 0.2 alpha version, added the latest Web of Science data into the cloud platform. Now the data covers all the way up to 2019. And you can reach us through all these different channels. I just want to acknowledge the support that we get from IMLS and Web of Science, Microsoft Research, and all of our supporting institutions with our latest edition in University of Maryland. A brief recall of what happened this year. The webinar series started back in February. Alpha launch at the same time. The fellow teams, the CADRE Fellows, has been running this webinar series since then. We started a new fellow program for coronavirus-related bibliographic research, and we have scheduled presentations of our fellow teams all the way through October. So please stay tuned and see some brief overviews of the previous fellow presentations. I'm just going to quickly go through them, but you can find all these past video recording in our website. And today our presentation came from a big group led by Russell Funk from University of Minnesota. They're actually going to present a double header since they're a big team and each of them have different aspects of the same project. Today is Russell's presentation, and Aaron from University of Arizona will present next week. So please come back. Stay tuned. And so here's a more sort of specific title that I think Russell will be presenting today. It's about, this is Aaron's presentation next week. Sorry about that. So this is a preview of what's going to happen next week. And you can find all our resources in these links. And without further ado, today's presentation is about sort of nature of innovation. That's a very exciting topic. Russell Funk himself will be the presenter. He's an assistant professor at the School of Management at the University of Minnesota. And without further ado, I'll start sharing here. And Russell, please take over.
Great. Okay, can you see my screen? Okay, good. Okay. Well, thank you to Shaoran and Stephanie and everybody else from the CADRE team for, both for giving me the fellowship opportunity and for all the support with the data and just the community and infrastructure, and for giving me the opportunity to share some of this work today. So this is really early stage work. It's a very much in progress paper. I think the presentation came at a really good time because we were just starting to have some results that are getting to the stage where we can present them and are ready for feedback. Having said that, so Sharon mentioned that we have a big team, and so there's two different groups that I've been working with who are on kind of our fellowship project. But I should also say too that this is kind of so hot off the presses that the other team members have not seen a lot of this. So, any of the bad ideas, stupid ideas, things like that in here, just, blame me. It's not the fault of the other team members because they haven't, had a chance to really sign off on this stuff yet. As far as the talk, so the basic idea is going to be looking at, it's mostly all just descriptive at this point, and maybe we'll just stay that way. I think it's kind of a useful approach for getting at some of the things that we want to look at. As Sharon mentioned from the title, we're trying to get at characterizing some of the changing nature of science and of innovation in science and technology as a way of maybe shedding some insight on certain debates that people have observed about innovation getting harder and so on, using some new data and some new methodological approaches. And by the way, if you have any questions, feel free. I'm not sure, I taught on Zoom, but I'm still kind of a bit inept when it comes to that. So if I see you waving or something, or if you want to just jump in with a question, feel free to do that. Or if not, hopefully there'll be time at the end for questions too. So as far as the roadmap, pretty much just the standard academic talk plan. I'll just start out with a minute, kind of giving you some of the context and the motivation for the set of analyses that we've been working on. And then one of the key things that we're doing in this paper that I think will help us hopefully shed some new insight is using a new measurement approach with some new kind of bigger data than has been available for addressing these questions in the past. And I'll talk then a little more specifically about the data. We're looking at papers and patents, so kind of two big but distinct data sets, and thanks to CADRE for help with that along the way. And then just kind of breaking up the results, kind of establish some patterns about the changing nature of innovation, try to characterize the change in terms of what's driving it or where is it happening most, and then try to propose maybe some potential explanations or tease apart, or at least see what the evidence is like for different kinds of explanations people have proposed. Okay, so the motivation is that I'm sure everybody here is aware of, or most people are aware of, that the 20th century, the post-war era in particular, was one of the most productive for science and technology in history. It had advances like discovery of DNA, development of quantum mechanics and artificial intelligence, all sorts of different things. But there's also been a growing stream of literature, some in more of the economics area, some in kind of science of science, scientometric studies. This points to a slowdown in innovation in science and technology, meaning that we're devoting more resources in terms of people, money, papers, investigations to science and technology than ever, but on a number of different measures and benchmarks that I'll talk about, it seems like we're making less progress. So there's less innovation, or less innovation that really kind of moves the needle over time. And so people have offered a number of different explanations for this, including the idea that all the discoveries that have been made, or that sort of all the low-hanging fruit is gone, like all the big important or easy discoveries that could be made kind of have been made. And so, there's a finite set of like big physical laws that you can derive, and that once they're gone, everything else just seems a little bit less important or much harder to get at. And also just as science has grown, it's sort of collapsing in some ways under its own weight, and that it's so hard for, there's so much that's known, so much literature, it's hard for people to actually master it all. It takes half your career to really learn a literature, and it's harder then to span fields and get to know different areas, which can help you come up with new innovations and new ideas. So those are just some of the explanations. This is obviously a really complicated problem, and people have proposed other things too, but just to give you some flavor. And so there's some different empirical support for this view, and people have done case studies of different fields and industries and so forth, and given support for it. But it's also, if you think about it more deeply, sometimes hard to reconcile some of those findings in even just the claim of science and science and technological innovation slowing down with things like theories of innovation. So one of the most common views of innovation and where innovation comes from is that it's a process of recombination. So things are seldom, if ever, rarely totally new, but instead they come from taking old ideas and knowledge and insights and bringing them together in new ways. And if you think about that, then if that's really where innovation comes from recombination, then the extent of prior knowledge is really important for driving future innovation. It lets us stand on the shoulders of giants And the more prior ideas, the more prior knowledge that we have, just the more potential combinations that we can make. If we only know a couple things, there's only so many potential new combinations, new ways we can combine those. If we've got a lot, there's a bunch of different things that we can try. And so, you would think that as knowledge has really grown, as we've made all this advance, it might one way of thinking about it is it might feed on itself and grow and enable more and more innovation. And that's just what's happened. So on virtually every imaginable metric, the post-war era has seen a bunch of increase in science and scientific and technological knowledge. And so if you think about it from that point of view, it seems as though there's a lot of the raw material to go into coming up with new ideas and innovations. Even if you set aside the theories of innovation, it's hard. If you just talk with people outside of academia that don't follow these debates, and you say, oh yeah, like innovation is really slowing down, sometimes they'll scratch their heads and they'll say, well, I just heard about, someone taking a picture of a black hole, or what about self-driving cars? What about artificial intelligence? What about measurement of gravity waves, right? And so, if you think about, well, just do those claims, even if we've got some evidence for them, do they really pass some of the, the basic sniff tests? Like, how do you account for all these examples of seemingly important breakthroughs that are coming recently with these broader macro trends that seem to indicate some kind of slowing down? And so, I think although, as I said, there is support and there's plenty of evidence that points to some kind of slowdown, there's also a lot of questions that remain and things that would be worth digging into more to try to better understand the nature of the slowdown. Like, is it uniform across fields? So one possible explanation would be, well, maybe some fields are really slowing down, but others are speeding up. What about researchers? Maybe the composition of researchers are changing. You have generational change and so forth, and if different generations have different approaches to research and styles, maybe that could account for it. And what about, so maybe are these, what's the temporal duration of these trends? Is it, very long term? Is this just a blip on the radar screen? And so forth. And so what we try to do is our basic idea is to use a new measure, kind of theoretically informed measure that I developed with my old advisor in a different paper a couple of years ago, to try to document long-term changes in the nature of innovation in science and technology. And then we try to characterize those changes by looking at differences across fields, researchers, and time. And then we try to reconcile the observed changes that we see and that have been claimed with theories of innovation, and try to see how we can have this explosion of knowledge that could be a good input to innovation, kind of disruptive, important innovation, with the fact that, in our measure and then in other places, it seems like we're not seeing the same types of breakthroughs that we used to. So, on the measurement approach, so just to mention a little bit more and give you a bit more concrete, some more concrete examples of, the prior measures that people have looked at in this area to make these claims. So people have looked at a lot of different indicators. A lot of them have been, they have plenty of strengths for sure, but they've also been somewhat indirect or field specific. So, on the econ side, people look at things like total factor productivity growth. Moore's law is kind of a favorite thing to look at, the number of transistors on an integrated circuit, and the number of scientists and researchers that were required to keep Moore's law going. Looking at things like agricultural crop yields, patents per capita, year of Nobel Prize winning discovery. So if you plot out the awards for Nobel Prizes every year, and you see when the discovery was made for those awards, even in recent years, they're concentrated not in the 2000s and 90s and 80s, but in the 70s and earlier periods. And so these are really informative measures, but it's difficult to address some of the questions that we had just proposed, like differences across fields. If your field doesn't award a Nobel Prize, you can't really use that measure to look at progress in that area. Moore's law is great for semiconductors and electrical engineering, but what does it tell us about the social sciences? And so what we'd really like to be able to make, it is a measure that is obviously not going to be as nuanced or maybe as immediately meaningful as some of these field-specific measures, but can at least let us get the 30,000-foot overview, look across a lot of fields, look across time. And so we want something that would apply to a bunch of different fields. That's also theoretically informed, that kind of builds on theories of innovation and points to different kinds of innovation that you would think would be important and worth measuring. And so there are obviously a lot of different indicators that have been developed that measure different properties of innovation. One of the most common that, again, I think we're all aware of would just be counting forward citations. So one thing you can imagine doing would be looking at, just papers that are kind of have an unexpectedly high number of citations relative to their field and year or so forth, and are those increasing or decreasing over time? And another would be some kind of measure of novelty, like new combinations, new words, things like that. And those measures all have their place, but they've also got some limitations. So it's sometimes hard for the forward citation or the impact types of measures. There's been massive increases in the number of citations that papers are making over time. And so it's kind of hard to, even if you normalize, it's kind of hard to, think whether you're making comparisons, apples to apples between different eras and different fields and stuff like that. There's also some ambiguity in how you interpret a measure of forward citations. It gives you some indication that a paper is being used, but in terms of what it does to push the field forward, or does it open up a new area, or does it kind of reinforce an existing area? What is the meaning of that number is sometimes unclear. And similarly with the novelty measures, those are also really helpful for certain things. But there's also, especially as science gets bigger and bigger and bigger, and the number of combinations we might make gets huge, there's plenty of great combinations that open up new areas and really move things forward, but there's plenty that are just bad combinations. And so it'd be nice to have a measure that you could make some kind of valence of this is better, this is worse, and so forth. So anyway, what we did a couple years ago is we tried to develop this measure that was based on kind of big theories of scientific and technological change. And the idea was that a valuable measure of an intellectual contribution would be to look at how it influences the use of prior knowledge. If you're trying to think of progress and the evolution of science and technology, then one way you can think about that is what does it do to, what is a new paper, a new patent, or new other intellectual contribution due to the things that it builds on. And so here's one way you can think about this. And we try to distinguish between two sort of poles. So one is that a paper or patent could be very consolidating when it kind of builds on and improves its predecessors and kind of makes them more valuable. So it's kind of complementary, right? So you get a new product that you come up with a new idea that maybe cracks a problem in an area and then makes all this other prior stuff even more useful, more valuable. The other would be, and so that's kind of, and I'll get to this in a second, that's kind of this side. The other is like sort of disruptive or destabilizing kind of innovations, as I call them. The ones that offer massive improvements or just new ways of looking at things over the state of the art, and they kind of render the old stuff obsolete. So you think of like the big innovations in biotechnology, recombinant DNA, things like that, as opposed to the old methods of pharmaceutical discovery, and so forth. And so so that's kind of the big idea, and that's not our distinction. The terms destabilizing, consolidating are things we use to kind of label these dimensions of the measure. But the idea that there's some developmental types of innovations that are very important, some that are kind of disruptive and destabilizing, is an old one in the literature. And so we were trying to think, well, how could you measure this? And what we tried to do is kind of distinguish between, first of all, kind of two ideal typical cases. And so you can imagine you've got on the left, can people see my mouse here? Or am I just pointing to nothing? Okay. So here on the left, you've got an example of what we call a very destabilizing or disruptive kind of discovery. And so here's a paper. Imagine this diamond is a paper, and it cites 4 things, right? And So what we want to do, if we want to try to understand the nature of the influence of this paper, is look at what are the future things that cite this paper do. Do they just cite the paper itself and not the predecessors, or do they cite the paper along with its predecessor? So if these future things cite the focal paper and the predecessors, as they do here, then that would sort of suggest some kind of complementarity, or that this paper did something to kind of draw attention to this body of work. Maybe it was a review paper or something like that. In this case, though, this thing comes along and then nothing else ends up citing the predecessors. So it's sort of like a categorical type of break with the past, right? So this offered major improvements over the old ways of doing things. This stuff only cites the focal paper. And so you can imagine these are sort of two ideal types. Now, one thing that's interesting is if you just look at these two papers, right? They both cite the same number of things, 4 things. They're both cited by the same number of things in the future, right? 6 papers. But you know, the nature of influence, the nature of how future work engages with this and the prior stream of work that this paper builds on, you know, is totally different. So on an impact measure, if we're just counting forward citations, these look the same, you know, but this might be something like a review article that synthesizes a body of work, whereas this is more like something that opens up a new field. Right? So that's the basic idea of the measure. I'm not going to spend too much time on this. This is just kind of the way that it's calculated. You know, basically we just kind of go through, all this is sort of doing is just, you know, you go through and you sort of try to do an inventory of, look at the forward citations and then count whether they cite, you know, the focal paper alone or the focal paper and the predecessors or just the predecessors, and then you just kind of sum them up. And so the measure will range from -1 to 1. -1 means that you are on this side of the spectrum. So you're maximally consolidating. Everything that cites you also cites something that you cited, right? If you're a +1, that means you're more destabilizing, or you could think of it as like disruptive. Everything that cites you doesn't cite the stuff that you build on, you know, so you're sort of pushing the development of science or technology in a different direction. And so here's just an example of the calculation. You know, so we just kind of do this inventory, we add up this, and so, you know, when you count these, you know, this works out to be -1, this works out to be 1. Here's one that's sort of in the middle. There are these 3 different types of citations. So something that just cites the past, the predecessors, something that cites both the predecessors and the focal paper, and then something that just cites the focal paper. And so if you calculate this out, this is sort of in the middle, the value of 0.17. And so we sort of think of the things that are in the middle as, you know, that have values at 0, closer to 0, as just, they just, you know, don't do too much to move the needle. They don't make the area that they build on, you know, more, they don't draw attention to it, kind of reinforce it, make it better or more valuable. They don't really, you know, chart a new course of technology. They're just kind of there, kind of in the middle. And so it's, you know, it's a fairly new measure, but it's been both in some of the stuff that we've done and then some research that other groups have done. It's received some pretty nice positive support in terms of just validity checks. So in terms of discriminant validity, you know, is this different from other measures? It depends, of course, on the data set you're using and what the nature of the documents are, the papers, patents, or something else. People have applied this to a number of different things, like, you know, music and software and other stuff too. But it tends to be pretty uncorrelated with measures of forward citations, and also tends to be pretty uncorrelated with measures of novelty. It's a bit more correlated with novelty than forward citations, but, you know, it seems to be capturing a different kind of phenomenon. But it also has, you know, fairly high convergent validity in that it does correlate with things that you would think it should correlate with. So one of the things we did in the original paper was a bunch of just case studies of important inventions in science and in technology. We're focusing on patents. So we looked at things like, you know, the PageRank patent and some of the early biotech patents and some things in, you know, agricultural biotechnology, and, you know, things that people had written about And we could say, okay, this is the type of paper, or this is the type of patent or invention that really opened up a new field. And so we would hope that it would correlate highly on the positive dimension of this measure. And we found support there. Another group, this Wuong and Evans paper, has done a number of validation checks looking at surveys of scientists and asking them to nominate papers that they thought were disruptive. And it was highly correlated with those. It's been highly correlated with external indicators of important work, like Nobel Prize winning papers tend to be positively correlated with the measure, so higher values on the disruption side. Review articles tend to be negatively correlated, so more on the consolidating side. The Wuong and Evans, they also looked at did some textual analysis, and we've been doing some more of this too. So the destabilizing, the types of papers that disruptive things tend to use words like change, introduce, advance, so pushing the stream forward. The consolidating works tend to use words like confirm, endorse, demonstrate, so kind of reinforcing the status quo that they build on, and so forth. And so, of course, any measure's got some weaknesses, but so far there's been, it's been reassuring to see some of these, validity checks. And so it's got, I'd say the main attractive features are that kind of fits well with theory. It captures this distinction that people often make. And then it seems to be correlated with the things we think it should be correlated with. Okay, so we're looking at two data sets. And the idea would be if we can track similar patterns across the data sets, that's going to add more confidence to our results. And maybe we'll find some differences across them that will add nuances to our understanding. The first one is the patent data. So we compute this measure that we call the CD index for consolidating and destabilization on patents. And we measure it. So as I mentioned earlier, there's been this massive increase in both number of papers and patents published, but also the number of citations per paper and patent. So we want to control for that. And we also want to control for just the amount of time that something is at risk of being cited and so forth. So and we do that with a number of strategies, but one of the basics that we do is we just calculate this measure based on citations received as of 5 years after publication. So for patents, that's 5 years after it's granted. For papers, that's 5 years after published. So the cumulative for the first 5 years. And the results are really similar if we use longer windows or do other things like that, but that gives us a little bit of standardization. We're using the USPTO Patents View database. We're focusing on utility patents, which is something like 90% of all patents. And that gives us about just shy of 4 million patents that are granted between 1976 and 2010. For a lot of our analyses, we're going to break things up by field. And so for our display, we'll use the high level, the NBER technology categories, which are things like chemical patents, electrical, and so forth. But then for our models, and when we can, we'll use some more granular subcategories. And there's about 38 of those, about 5 if you exclude other of the top level categories. For papers, we're using Web of Science. Again, we're computing the measure 5 years post-publication. We're focusing on English language journal articles. And we've got about 25 million papers. That leaves us about 25 million published between 1945 and 2010. For the fields here, we're using Web of Science categories, the kind of top level fields that we'll use just for our presentation, or the research areas, as Clarivate calls them. And then we're using the extended subject categories for more kind of granular fields, and there's about 100 of those. Okay, so that's a lot of buildup. Now to getting to some results in data. So this is, probably the key slide. Everything else is kind of trying to unpack this. And so what you have is on the left-hand side, you've got papers. On the right-hand side, you've got patents. The x-axis on each of these graphs is the year, and the y-axis tells you the average value of this CD index over time by field, right? And so, I mentioned earlier that there have been these claims about a slowdown in scientific and technological innovation. And to the extent that you think this, you're convinced, or you buy my arguments that this CD index captures an important characteristic of innovation, and you think, that important innovations that kind of push the field forward would score higher on this measure, right, on the more positive side. Then what this is showing is that there's been a really substantial decline in both papers and patents over time. So if you look at the average CV index value across these fields, it's declining in all the major areas: social sciences, technology, physical sciences, life sciences. There is some notable variation I'll talk about a little bit as far as for papers in terms of the fields, although if you look at the overall trend, kind of the slopes, they're fairly similar. Patents, surprisingly, there's a lot less variation by field. I guess that's plausible given that patents are overall, even though there's different fields, a more homogeneous kind of document than scientific papers. But so on the surface, this is very consistent with what you would expect given some of the research I cited earlier about the slowdown or kind of the changing nature of innovation. Okay, so the next step then is going to try to, the next few slides, what I want to do is try to just unpack this a little bit and figure out what's going on. And actually, so the reason I first started thinking about this was when we were developing that measure. So I was still in grad school then, and was just doing a bunch of plots, and I just happened to kind of plot it over time, more just to make sure the data were making sense. And I saw this, we were doing patents, this just dramatic decline, and that kind of always stuck with me. It was kind of too much to include in the paper, and so, but I always wanted to understand what was going on. And so one of the first things I did was I thought, well, there could be two reasons why, or that there could be different reasons why you would see the measure decreasing over time. So just first of all, notice that this is all kind of in the positive territory, which makes sense too, if especially for patents, but even papers, we're often publishing things because we want to move the paper forward and improve over what's done before. And so, it's not that surprising that, the things that do get published are more kind of destabilizing or disruptive. But you could imagine that, one reason why we're seeing this move towards zero is that everything's becoming more consolidating. So everything's kind of looking like, it gets cited together with the stuff it builds on and kind of reinforcing these trajectories. And so that's a possibility. And so one way I tried to get at that was just by splitting the measure. So everything that had a value above zero and below zero, and plotting them separately and seeing what that looked like. And so here are the, so if you split it above and below zero, you could sort of say that the ones that are above zero are the kind of destabilizing, disruptive types of papers and patents. And the ones that are below zero are the consolidating, kind of, reinforce the area. And it looks like it's not that everything's being pulled down by becoming more consolidating, it's just everything is going more towards zero, right? So there's kind of like less the fewer papers, or papers to a lesser degree, are kind of disrupting the streams that they build on, but also kind of consolidating them less too. And I think that's interesting because you can think about both of these dimensions. I think we tend to think about the disruptive side, and we talk about disruptive innovation a lot. We tend to think about those as like, that's what innovation should do. But certainly there's something to be said about consolidating innovations, and those can be just as difficult and be just as important as well. A lit review that brings together different areas and kind of revitalizes them is very important too. And not that these are all lit reviews either, but. Okay, so, another thing something that I've also been curious about, and you might wonder, and this is an area that we're trying to work on more, and I've got some ideas of future stuff, but is this all, like, what if this is all just the measure? I mean, it's as I said before, there's some reasons to think the measure is, picking up on some useful properties and passes some basic validation checks. But, what if, how much stock should we put into that? And so, I've been looking at a lot of other measures and trying to see whether we see similar patterns in them. And to the extent that we do, then, that would suggest, well, it's not just the measure that we're seeing, where we're seeing this. And so one of the things that I did that kind of stuck with me and that I wanted to share was looking at some textual data, right? And so so what we did is we took, using some of the CADRE data and the patent data, our thinking was that destabilizing or disruptive sort of innovations are making a break with the past. They're introducing new things, trying to change the status quo. And to do that, you've probably got to use new words, right? New vocabulary to describe things. And then if you're building off of one of those types of papers too, you're going to use new terms to describe this new phenomenon that's different from prior ways of doing things. And so what you might expect then is that in fields where you have a greater proportion of destabilizing or disruptive papers, that you would see richer language, more diverse vocabulary usage. And so what I did here is I just pulled the abstracts and the titles of papers and patents. The patents, we go back to about 1980 for these, and the titles for the papers, we can get back to like 1945. Abstracts, the data isn't quite as good, it seems, for earlier eras. And then just compute a measure of lexical diversity. So this is basically the number of unique tokens to total tokens. So how many distinctive words are you using the same set of words over and over again, or using a rich set of words? And you can see it was interesting to see that these track pretty well onto the patterns that you see in the measure. And what's neat about this is, again, you might think, well, the disruption index, maybe it's due to changes in citation practices or number of citations. And so but the abstracts and titles would not be dependent on citation data. And so it's kind of a nice, reassuring kind of sanity check to see, okay, well, here's a prediction we can make, and for what we would see in a different measure, and we see similar patterns. Now, another question that I had was whether this could be related to changes in the quality of publication, right? So maybe, in earlier eras, people just published a lot less, and so then when they did publish things, they tended to be more important contributions that really push things forward. Maybe the costs of publication have gone down, and so there's just a bunch of low quality publishers that will publish anything. And so what is really, so that would be an alternative possibility that, might probably not be quite as interesting as if we're seeing some kind of change in the nature of innovation. And so this is, again, something that I'm trying to dig into a little bit more, and I've got some additional ideas. But as a first cut, what I did is I just took, 3 very prestigious journals, PNAS, Nature, and Science, and thought, well, presumably the quality of what they publish has been relatively stable over time. If you look within journal or high impact sort of journal, it would be less likely to be driven by new kind of fly-by-night publishers just publishing anything. And so here again, we see essentially exactly the same pattern that we've seen before. This is just the average of this measure, this CD index, by year, and it's the same sort of decline that we saw for the whole sample of data. So here, okay, so that's kind of just trying to unpack the trends a little bit. The next set of results that I wanted to share are trying to kind of get a little bit closer to, some kind of explanation. I mean, I still think these very much is descriptive, but trying to see, okay, here's some different explanations that people have proposed, and here are some things that, we propose, what descriptively even, just what, do we see anything that's consistent or inconsistent with those? And so, so one of the explanations that I mentioned before is that, we're running out of innovations to be made. And, I've been kind of thinking of this explanation. So this is, so the low-hanging fruit is gone, or, a different way you could think about this that I've, metaphor that I thought about when I was putting this together is kind of like, innovations is like a mine, right? A gold mine. You go into the ground, you pull stuff out, eventually you'll run out of gold, right? You'll dig everything that's out of there. Or there might be some, but it's going to be in the really hard to reach places, and so you're going to require more, fancier tools and more people to go and get it, right? So is that the right model to think about innovation in science and technology? And so I do think that there's definitely some plausibility to this. If there's a finite set of laws of nature or fundamental particles to be discovered, you can only discover them once. And so once those are gone, everything else might just seem a little less significant, right? Or maybe is a little less important. There are some arguments against this view. So this is a nice recent paper that was on the NBR working paper site that talks about, they give a bunch of examples of people saying this exact same thing, like in 1900, that like, no one's going to have a career in physics anymore because we already know anything, you know? And so, you know, and yet look what happened in the 20th century. You know, there's also the kind of combinatorial explosion argument that I made before. I think we can start to get at this a little bit with the measure that we're looking at is kind of indirect evidence. And again, it's something I'm kind of working on, but it's worth kind of digging into. So how might we do that? Well, if the gold mine is being emptied out, right? You could think about what kinds of patterns you might expect to see in the data, and you might expect to see declining, you know, destabilization over time. These big disruptive kind of innovations, which is kind of consistent with what we see. But you might also expect to see some certain patterns in, you know, what accounts for the any variation remaining in that index that we see. So what do I mean by that? Well, for example, you know, it seems like if scientific fields and technological fields and innovation in them is like a mine, then you could think of them as probably separate mines, right? Or maybe loosely connected mines, right? And we're pulling out the ideas from them. Eventually they'll run dry, but it seems like unlikely that they would all run dry at the same time, right? So what is the reason why the social sciences would have made all their, you know, great discoveries at the exact same moment, or, you know, around the same time that, you know, the physical sciences would? I mean, the fields have started at very different times. They've had different resources, you know, random chance. It seems unlikely that those patterns would track highly onto them. But if it is the case, yeah. So so you should, in other words, expect to see that field would be a big predictor, right? Because if they have different, you know, the different mines at different depths and all that. You might also think that year, you know, when a paper was published would be a very good predictor, because, you know, again, if the mine has sort of a finite amount of stuff in it, then, you know, it doesn't matter how many resources you put into figuring something out, there's only so much left, and the longer you can add it, the less there is, right? And so what I did is just try to decompose the R squared or adjusted R squared for some different regression models, predicting the CD index from author by paper, author by patent observations. So this ended up being a massive data set that started to blow up my computer, but the Web of Science one has something like 84 million observations in the regression. But so that's all this is. So CD index is the outcome. The predictors are just fixed effects of field or subfield, author identifiers, and then years. And then we can use this technique, this like Shapley-Owen decomposition, to try to see how much each set of predictors contributes to the overall R squared, right? And so interestingly, it's easier to explain, or we can explain more variation overall in patents. The R squared from these fixed effects is higher than papers, which again makes sense given that patents are kind of a homogeneous sort of thing relative to papers. And, you know, I mean, to the extent that my proposals earlier are right, that, you know, we should see if it's this all the low-hanging fruit is gone sort of thing argument, you know, we actually don't see that much variation explained by field. And so knowing the field, which you would think would probably be important, doesn't seem to be that important. Year, when, seems to be actually fairly important for patents, but not so important for papers. You know, instead, what's the most important for both, though, is the author. So just knowing who the person is that's on the paper or on the patent, rather than you know, when it was published or what the field is. And so I think, and you know, this is an explanation I'm still working on, but it seems to me that that's, you know, if we're running out of all the low-hanging fruit, that shouldn't really matter as much. So in other words, like if the gold mine is empty, it doesn't matter if you send Albert Einstein in there or some random person, they're still not going to come out with something right. And so that seems to be somewhat inconsistent with that. Okay, so the last bit of analysis that I wanted to share was a potential alternative explanation that tries to reconcile some of the observations I made earlier about theories of innovation and recombination. So science has grown massively. There's more ideas, more papers out there than ever. And if you think about innovation as this process of recombination, there's so much stuff that you can just grab and pick up, and we've got information at our fingertips. And shouldn't that give us the opportunity to make so many new, come up with so many new ideas, and shouldn't this be the golden age of innovation? And again, this is not saying this is like the full factor that explains this, but it's a very complicated phenomenon, but just one possible explanation. And so I think it's somewhat difficult, or worth exploring at least, that, how do you reconcile this decline that's been proposed and discussed, and we see evidence with, of this explosion in publication? How does this fit with the idea of standing on the shoulders of giants and so forth? And so one possibility is that although we have more science than ever, if you measure knowledge or think that papers is maybe some even rough proxy for knowledge, then there's also some evidence that suggests we're using less of it over time, right? So the more you have, maybe the less you use. And this is something that prior work has suggested may be a possibility, but as far as I know, it hasn't really been related to these debates on the slowdown of innovation. So here's just a demonstration of the volume of science and technology increasing. I think I'm sure the folks at CADRE that have been working with the data know this, because I know where any analysis I run, it's like once you start to get to the year 2000, it's like everything just slows down because the data just gets so big. But so these are papers published not cumulatively, but this is per year, right? And patents granted, again, not cumulatively, but per year. So there's just been a massive increase. But if you look at various measures of utilization of work, of papers, patents, and so forth, there's a pretty consistent message, and we have others beyond these. These are just some that I picked out, that it is decreasing. So here's, again, for papers, top row, patents, the bottom row, a measure of the diversity of work cited. So at the field level. So this looks at collectively the set of works that papers or patents in a field are citing, and it's essentially a measure of entropy. And so when we see this decrease, that's suggesting that more papers are citing a smaller number of other papers. So they're concentrating their citations essentially in a smaller number of prior work. So you got a smaller set of things that are highly cited and more other things that are not cited as much. And so that less diversity, higher reliance on the highly cited stuff would suggest maybe less utilization. There's also been this dramatic increase in self-citations per paper, and even in patents. And so we see this across every field. So today something like there's 4 self-citations in physical sciences per paper, life sciences, and so forth. And again, that you can think of that as maybe a rough proxy for breadth of search or search depth. If you're citing yourself a bunch, it's probably not novel information for you. And then the last is the age of stuff cited. So I think this kind of makes sense if you think about this with the diversity of work. So the age across fields of prior work cited, if you look at the average age of things cited, it tends to be going up quite dramatically. And this holds even if you adjust for the fact that as time goes by, stuff gets older. So it doesn't really matter if you account for that or not. And I think if you look at these together, it sort of suggests we've got classics in a field that are getting cited a lot, maybe newer stuff, less popular stuff getting cited less, and so maybe an indicator of less utilization. And so our last thing is going to be to just run a simple regression where we have these as predictors. The variables I just suggested, the outcome is a CD index, run it on patents and papers with fixed effects for the publication year subfield, and just see if there's any evidence, these are just descriptive stats, I'm gonna skip these, about to support this idea of utilization mattering for disruptive destabilizing discoveries. And the predictions are pretty much with what we would expect. So in fields where there's more diversity, diverse work cited, the average, the conditional average CD index is higher. In fields, in papers that make fewer self-citations, it tends to be higher. Papers that make more self-citations, it tends to be lower. And then the age, generally what we see, so the interactions are a little hard to understand if you kind of plot out the values and look at them. For patents, or for papers, we tend to see that the ones that have the highest predicted CD index are ones that cite older stuff, but with a greater variation in the ages. So it would kind of suggest, you're building on the established things, but then maybe, taking knowledge from and utilizing knowledge from other areas. The results for patents on the age stuff are a little less clear, though, and we need to dig into them more. Okay, so last analysis, and then I'm done, and we'll move for questions. So is on the thing I mentioned at the beginning. If you just talk to your family over the dinner table and say, oh, innovation is like slowing down, they'll be like, well, what about self-driving cars and the internet and all this other stuff? And so, how can you reconcile all those examples with some of these macro trends, not that I've shown you today, but you see in other areas? Is there a way that both can be true? And this is, again, something that I think this measurement approach can try to give us some insight to. And so this is another plot that, again, I'm still trying to work through, and this is like a hot off the presses thing. But basically, what I've done here is for papers and patents, I've just plotted the number. So I've split the CD index into bins, and this is only the positive dimension. So you have 0 to 0.25, 0.25 to 0.05, 0.5 to 0.75, 0.75 to 1, and then just plotted the number of things in those buckets over time. And what's really, really interesting is that, and keep in mind, we saw how dramatic the number of papers and patents has grown over time in these areas. It seems as though there's this very constant a constant number per year of papers or patents that are highly destabilizing on this measure. I mean, while the number of papers and patents has increased dramatically, it's been very constant over time, the number that are at the higher end of that dimension. Whereas what's really increased are the things that are at the lower values that kind of don't move the needle quite as much. And so anyway, this is something that I am hoping to unpack a little bit more. All right, so just quick wrap up. The motivation was the 20th century has been, and 21st century, has been a super productive time for science and technology, but people have also suggested that things seem to be slowing down. And that's a big claim, a very important claim. And people have proposed a number of useful and very thoughtful explanations. But there are also a bunch of unknown questions that I think are important to investigate for a problem that's this big. And so the idea here was to take this new measure that's got some nice attractive features and see if we can use that to make some comparisons across field over time and kind of get some insights that maybe are difficult using more of the field specific indicators. And so we kind of broke things down across science and technology, tried to characterize the nature of innovation using this measure, tried to decompose some of the changes according to researchers' fields and so forth, and then tried to do a little bit to reconcile some of these measures of innovation. Last thing is, if you're interested in the measure, there's a Python package and some data and other stuff available that you can email me if you're interested. But thanks so much, everyone.
Thank you, Russ, for the wonderful presentation. And we have about 5 minutes for questions. Before we go there, I just want to briefly launch a poll for the attendees today for our survey purposes. Any questions, feel free to ask.
Hey, Russell, I have a question. I can start us off. My name is Jackie Wilkinson. I'm the project director of CADRE.
Hi.
Hi, nice to meet you. This data, especially your final slides about, you know, the rate of publications and potentially their lack of, you know, destabilizing quality within the scholarly publishing field. As someone who's a librarian, this is something that's very relevant to a lot of conversations and critique that I've been hearing recently about CV padding and some critical analysis of scholarly publishing as a whole and academia as a whole. And I'm wondering if you have plans to kind of connect this research to larger trends like that, or if that's a part of your scholarly interest.
Yeah, I think that'd be really interesting. And you know, so I guess, like I said, some of the stuff that I have been sharing with you has come together very recently, and I've been surprised myself by some of these findings. I mean, I guess I really thought, and I don't think by any means I've demonstrated this yet, but I thought that a lot of it would be due to changes in quality. Like, you know, people just, the pressure to publish, and there's so many places that you can publish, and, you know, just things coming out that, you know, just aren't meant to and don't really, you know, move the needle all that much. You know, I think so far some of the evidence that I've seen suggests that that's not totally the case. You know, as you see with the, like just the plots of the PNAS and science and so forth, that it seems to be affecting them too. I've looked at things like the just separated out by journal impact factor. Something else I want to do is look at, you know, the Nobel Prize winning and other sorts of papers and see if we see it there too. But I think it's really interesting, and, you know, it does raise a question of, I mean, so to the extent that we do see that there's aspects of quality and so forth that's tied up to it, it kind of raises the question of, like, you know, do we need to slow down, right? Are we publishing too much, and would it be better to, you know, not have as much out there? Maybe that we could all read more, utilize the science and so forth, as opposed to just citing the same old things, and would that help to kind of move things forward? Or, you know, at least should we rethink some of what we're doing, the way we're doing it? If that's part of the problem, because I do think there is evidence that it's not that the gold mine is being emptied. It's at least a bit, part of the story is about the practice of science. I would say that's a great question.
Thank you.
We have time for perhaps one more question.
Looks like Aaron's saying something, but I can't hear.
Yeah, please unmute yourself if you have a question.
Sorry, I was muted. I have a question, but I'm on the team, so I'm happy to defer if there's someone else who has a question. And I have lots of questions. Anybody else?
Go ahead then.
Okay. Bunch of things we can talk about later too, Russ. One is this, you know, we've been revisiting Kuhn, Gina and I. Is this a story of maturing sciences, greater consensus, bigger core? Essential activity is one thought. I was intrigued by the author Fixed Effects and their author's critical role, the decomposition of the R squared. That's awesome. And I've been thinking recently about looking at the CD index at the author level, right? And even, is there a lot of variation with it? Am I a D person? Someone else is a C person? Are we all, do we all kind of do different papers of different types? I think is really intriguing. And then, well, I have other questions, but maybe the big one is about, and I've seen this in some of the analyses we've done too, relatively low, maybe not for the social sciences, but relatively low R squared values. This is an awesome story. There's a lot going on here. You've found some interesting results, but there's still so much we don't understand. There's 90%. So 90% of the variation in the CD index, we don't know. We can't measure. We haven't. So it'd be fun to, I don't know, try to step back and think like what's missing. And there may be a lot of stuff missing, like their social sciences, notoriously low R squares. We have a very difficult, you know, high bar kind of job, but it would be fun to think about that. And then my last point is the so-called the sweet spot thing. Was that consistent with UTSI? Was it the low? What is the sweet spot again? I can't even remember. I think it's the citing. Is it older, high mean low mean age, so more recent work, but greater variability.
Yeah, it's a little different. I think his is, you found similarity with it. I think his is low mean, high variance, and I think ours was like high mean, high variance. And I think, so he's looking at a different measure. I think it's, he's looking at
citation counts
too. It cited a lot, which might make sense that you're building on more recent stuff on average. I think to disrupt stuff, it's got to be established. If you're moving things forward, it's probably hard to disrupt something that was discovered yesterday when it's, what are you disrupting, right? I mean, it's not even there. So I think it makes sense given the different outcome measures that we see.
I think so too. It's just, it's a nice kind of, addition to that conversation, right? So yeah, anyway, cool.
Yeah, no, and I think my thought is with just the R squared, there's always something that's going to be random with discovery, and some of it depends on nature too. It's not just what we can do as people or researchers, and so you're probably never going to be able to explain everything, but there's definitely a lot to look at. So
yeah. Anyway, that's great.
Well, we are running out of time, but thanks again for a wonderful presentation, Russ. Russ, please send your materials to us. We can help you post them on our website so people can find them more easily.
Yep, we'll do it for sure. Thanks, everyone. Appreciate it.
Okay.
Thanks. Everyone for joining us today. Please come back next week for Erin's presentation.
Yes, please do. Thank you.
Thanks, everyone.
That's good. Thank you.
Bye, Russ.